Okay, so now, so this module is going to look at 2D FEM, okay, which is basically an extension of whatever we have looked at in 1D. So, this is the sort of flow that we will go through. Something sort of significant over here is we are going to directly look at vector finite elements. Okay. What I have shown you so far are node based in 1D, and I showed you the shape functions for node based in 2D. Okay. So, what we will do is we will directly jump to vector based finite elements, because you can, it is easy for you to follow the logic of 1D to 2D scalar. So, let us do something more interesting, 2D vector, or the other word for it is edge based. In the text it is referred to as node based and edge based. Okay. So, let us look at the kind of shape functions that we have. Okay. So, what was the kind of scalar shape function that we had? This is just to refresh your memory. If I had nodes 1, 2, 3 and some point P in between, right. So, I had defined Li as what? Area of so let us call it L1. L1 was area of P23 divided by area of 1, 2, 3, right. Right. P belongs to triangle P outside. Okay. And for example, Li of x comma y, it had turned out to be a linear function, right. So, we had for example, ai plus bix plus ciy by 2 triangle, right. That is what we had defined as the shape function. So, this was node based, and finally, with this what did we write? We said that the field anywhere inside u x comma y was written as some u1 L1 xy plus u2 L2 xy plus u3 L3 xy, right. So, the 2D node based thing is very simple, right. So, let us just write this over here, this is node based 2D. Okay. So, any value if you take inside, I can write it as a linear combination of u1, u2, u3, and these are linear functions. Okay. So, now the question is, how do I try to construct vector functions out of this? So, again here is the situation where the answer is a very beautiful geometric answer. So, I'll write it out and then we will see what its properties are. Okay. So, I am going to define a vector function t. So, it is a vector function, that means at any point in space it will have a magnitude and direction, right. Unlike this function L1, L2, L3, which at any point just has a magnitude, it is a scalar function, right. So, this t, let us call it k, it will be a function of x, y. I define it as, so Lk is the side of, is the kth, I mean the length of the kth side. Okay. So, k can be 1, 2, 3, fine, and Li okay. So, notice where the vectors are coming in from, right. I am taking a gradient of this, right. So, before you get into any details, what degree do you expect this to be? It will be linear only, because when I am taking the gradient, they are first order, they will go to 0 and then I will be left with Li's, right. So, again there are some very nice geometric features because of which all terms cancel off and you are left with this expression. So, Lk 4 triangle square, remember triangle is the area of the triangle, what is? So, this is a definition of vector shape functions. So, you will have T1, T2, T3. L is the length of the, is the same as above. The same Li which I had defined in the node case I used over here, right. So, length of,
that is the result from the node case.
yes, I am using that to build the next thing. Okay. So, it is interesting to note that in the x component there is no x, in the y component there is no y. Okay. And that just happens because of the way in which this thing is designed, these the x dependent terms cancel off. Okay. So, writing this expression like this, you do not get much intuition of what does it actually look like. Yeah. So, for example, T, say T1 will have length of 1. So, we will call this as L1, L3, L2. So, let us write this fully out over here. So, 1, then this is 2, 3 minus. So, why would you use node based or edge based, right. So, we will come to that towards a little bit later, but basic idea is Maxwell's equations are about vector fields. So, by putting the solution in terms of scalar functions, you lose a little bit of accuracy. Okay. So, vector based formulations are much more accurate. There is a problem called internal resonances, which happens in the case of node based formulation, where you get some spurious solutions, which physically do not exist, but they appear when you try to solve the system of equations using node based. Those go away when you use edge based elements. Okay. Right. So, this is what these basis functions look like. Okay. So, for example, this is your T1, okay, this is your T2 and this is your T3. Okay. So, as I said, at any point in space x y there will be a vector. So, therefore, a magnitude and a direction. Okay. So, I am writing the field at any point as a linear combination of these three vector fields. So, before we go into that, let us look at some of the properties, okay, two main properties. So, the first property over here is, if I look at, for example, any one edge over here, let us look at T1. So, remember this was 1 and in our convention this was 2 and 3. Okay. So, when I look at for example, T1, right, in this example, you can, you can from the figure you can sort of see that the component of T1 along edge 2, 3, what does it look like? So, T1 along edge 2, 3, component of T1. Well, for one is changing direction, once is starting out on the right, then swinging to the left hand side. So, yeah, the figure is slightly not very, it is not possible to determine this from the figure, but if you do the calculation, it turns out that the component of a vector field along the edge is constant. So, for what I mean is T1 dot r hat 2, 3 unit vector along 2, 3, and in fact it is the whole vector field. So, I am evaluating it at these points, at any point over here, right, at any point along these dotted things. If I take the component, I get 1. No, on the edge, only on the edge, not inside. Okay. That is the first thing. What about T1 along the other edges? So, edge is 1, 2 and 3, 1. What do you think it looks like? Normal, right? It is purely normal, there is no tangential component. Okay. So, what do you think might be the advantage of something like this? Yeah, so T1 does not at all corrupt the tangential component of the field along the other two edges. So, T1 takes care of the tangential component of edge 1. By edge 1 I mean edge 2, 3, right. And T2, for example, over here, T2 talks only about, T2's contribution along edge 2 is 1, along other edges 0, right. So, here for example, I should write this as 1 3 is equal to 0, T1 dot R 1 2 is equal to 0. This above thing may be plus or minus 1 depending on the convention. Okay. We have to be careful about that. So, when I do this, now I can write down field at any point inside. How can I write it now? So, u is now a vector x y is equal to, so I can write it like this, u1 t1 x y plus u2 t2 x y plus u3 t3 x y. Linear combination, that is how I am going to write it. So, I have, so why does this, what is the advantage of doing this? My unknowns are the tangential components of the field, right. If I go along any one of the edges, what will I get? I will get 1 or minus 1. So, I just multiply that by u1, u2, u3, and these are my unknowns now. In the problem that I formulate, I said I wanted to do a vector based formulation, that means my unknowns needed to be vectors. So, I wanted my unknowns to be vectors. So, what I have done is unknown vectors I have written as a scalar unknown multiplied by a known vector field. That is easier to solve than everything being unknown, right. So, unknowns now are scalars. What are the scalars? u1, u2, u3. Okay. Any other advantage that you can see of having done this? Hint is to think of more than one element. Yeah. So, these are all 0 outside. So, something about common edges. What is a nice property of these things? Automatically take care of tangential boundary conditions. For example, now supposing I have one triangle over here and another triangle over here, right. So, we know Maxwell's equations say that the tangential fields at any boundary are the same, unless there is some pure surface current. Let us ignore that for now, we can deal with it later. So, if I have, let us say, free space from here or some homogeneous, even a heterogeneous material, it does not matter. At any boundary interface, tangential fields are satisfied. So, if I take the basis functions inside this first element 1, let us say, and element 2, along this edge, if I assign the variable to be u1, then that u1 is common for element 1 and it is common for element 2, because that value u1 is shared. It is like what we had in the node based 1D FEM, the value at the node is common to both elements. Why create two variables? One variable, right. So, tangential boundary conditions automatically satisfied. Okay. So, this is people went through a lot of effort to make these, to construct these so as to have these properties. It is not just a happy coincidence that it happened, they designed these basis functions to have these properties, because if you are getting boundary conditions being satisfied for free, your solution is bound to be more accurate. Okay. So, these basis functions, they go by various names in the literature, right. So, I will just write down some of the names. They are called Whitney elements by one community, and another community calls them Nedelec elements. Yeah, so the question is that if I have two adjacent what do you call triangle elements, then what about the direction of these arrows over here? Yeah, so that will come to when we get down to implementation. We have to make sure that along a particular edge there is a consistency in which direction the vector field is going. Yeah. So this all gets taken care of under local to global conventions, right. So in FEM a lot of time is spent on making sure that when I go from local to global and global to local, everything is consistent. Okay. In fact, that is a source of a lot of coding mistakes also. Yeah. So we have to make sure that there is a consistent direction of the field along a given edge. It can't be that one element is saying this way, the other element is saying this way, because the unknown u1 is common to both, yeah, and there is only a unique direction to the field. Okay, so everyone's comfortable with these shape functions. So this is probably the first time you are looking at a vector field which you have constructed, right. So as I mentioned earlier, the advantage of this is that you get much better accuracy in representing your solution. And for example, the scattering problem which we did in the integral formulation, our unknown there was Ez, TM polarization. The same problem if I want to solve now, my unknown can be H in the plane, Hx, Hy will be written in terms of these vectors. So I need not work with Ez, I can work with H. When I travel from 1 to 2, yeah,
that side.
the tangential components of T2 and T3 are, no, when you are going from, you are saying I am walking from node 1 to 2, okay, and yeah, take any edge and walk along it. There is only one guy with a tangential component. Yeah. Everyone else has normal components. So the tangential component is only being given by that one component. So this is in contrast to these fluid mechanics people, where their constant component along a certain edge is not the tangential part but the normal thing. So that allows them to conserve flows across a boundary. In our case, we don't have a flow. Alright, so now let's yeah, question? Previous slide? Why is there no x in the x component and no y in the y component? That's just how it turns out once you do the algebra. Okay, I am writing down the final form, but if you, I mean these AIs, small a, small b, small c, they all have the coordinates of the triangle inside it, right. So they get involved in constructing this definition, okay. So you can work it out, they all cancel off, you are left with this very simple form. Okay, it's a little counterintuitive and surprising, but that's what it is. Okay, but it's a simple exercise in algebra to get it.